Hello, my name is Daniel Ayer, and this is my Task 3 video submission for DS685 here at NJIT, discussing Visual SLAM. And in this case, we're talking about VSLAM integration with ROS2. So here we have a tutorial and demo video that I'm going to make. Now, VSLAM, you can look up for all the technical details, but what we're doing is taking a series of images, either from a live stream cam or a existing video file, or a stack of images. We're identifying points in those images that we can use to track and then use that tracking to determine whether or not the camera has moved and moved to where. Now, if you go back into optics, you can go through very complex explanations of this, but it's very simple. If I'm standing looking at an object and those points are in my field of view and I move to my right, left, rotate, whatever, those objects, those points will rotate with me depending on the geometries of the world and how I've moved. And in our case, the camera that I'm using to record, you can imagine if I have a fisheye versus a regular with different configurations, those points will move in different ways. Now, we want to integrate this actually not with a camera per se, but with a robot with a camera. And since we don't have the money to buy a robot with a camera and run it on a space, we're going to integrate it with RViz in a gazebo environment, and a gazebo turtlebot environment, a manufactured artificial space in which a robot will move around in the space. And then let's walk through that. So here I am in my workspace, my turtlebot maze workspace, and we're actually going to need to spin up a couple of things. First, we're going to spin up our Xeno router. Xeno is a publishing structure which allows us to you can publish streams to it and subscribers can pull those streams down. So if I'm a CO2 detector, I can send a stream to Xeno saying I am detecting nothing or something. And anyone who cares whether or not there's a fire in that space can subscribe to that detector and be alerted if and when it publishes, oh no, there's a fire. In our case, we have a robot that is sampling images from the space, publishing those images to Xeno. We are going to capture those images and run VSLAM odometry on those images. So first, let's run our containers. Compose. Now we've been given a bunch of containers in this assignment, and these are all existing containers that work for us. What we want to do is fire up our Xeno router. Then we need a Xeno bridge. And then we need a world, demo world. We need a world to supply us with data. So let's let all this run. I really do like watching scrolling code. It's very nice. Here is our gazebo environment. Oop, come on now. Be populated. Okay. And does this make sense to us? Maybe it does, maybe it doesn't. Let's turn on our camera. And we can see here an image brick wall. So what have we done? Well, we've spun up this space. Might make a little more sense. And in this assignment, this has been supplied to us, and we have inserted objects within this world, person, benches, things. And here's a robot with a camera at a certain height that can see these. And right now it's just pointing at this brick wall. If I tell it to go, maybe go look at this person, you can see down here that the RealSense camera is picking up different images because the robot is moving, right? Those images are published to Xeno. We're going to grab those images and process them. So we've got our world running, but now what we need, no, okay. Now what we need is Docker compose up map stream. So we're going to run our Docker container that will map our stream. Okay, here's our map video. Here's our map stream. So just briefly, we have a Docker file that's going to make sure that everything's installed as it should be, as we need it to be. Our VSLAM Docker file. Okay, so this is our repo that we're pulling from, and we want to install Python, FFmpeg, Docker. I think some of these we don't need anymore. They were all part of the development. Rosbags, Eclipse, Xeno, OpenCV, NumPy, and Matplotlib. We're going to use these to visualize our map in real time as it's created. That was a bit of a trick. Then we had to enable this X11 for Docker to generate windows, and I actually integrated a Docker server into my terminal, so all terminals will have it. Sorry, Docker X11 server, and I made a little note every time you fire it up. Hey, close this up because X11, I'm to understand, is a security hole. We're going to mount our host space all the way up to VSLAM as data. We're going to run Python, and we're going to run vslam.py within that Python, which I wrote. Here it is. Now, what did I do? We have a Turtlebot RealSense Mono YAML configuration file that's for the camera. That's trying to accommodate for what images that we're getting in the camera that's capturing them. Then those are being published to a Xeno topic called camera raw image or image raw. Now the min matches is the number of matches we want minimum to track an image, and because of this synthetic environment, I had to drop this down quite a bit. So it's down to 15, and I think it works okay. If I bump it to 30, you get a lot of loss, and it doesn't work that well. We have a motion threshold and a rotation threshold and this one too, the rotation threshold, I just had to tweak manually until I got something usable, and we got it at 0.7. And then we want it to save every 100 images, or run the VSLAM on every 100 images. And I think that the Xeno topic is publishing at 5 frames per second. So how did I do this, or what's the architecture here? This architecture, I don't know if I can recommend. It's my own vestigial code bias from working with PHP and JavaScript. I like to create a class and encapsulate all of the business logic within that so that it's extensible out to multiple instances. This is highly not extensible. As you can see, it is very hard-coded, needs a lot of refactor, but at least the bones are there. The downside to this is it does tend to lead to race conditions and multi-threading issues that maybe this isn't the best setup, but here we are. It's what I did, and it worked. So within this class, we have our CV2 orb. We have our focal, from our calibration file, we have these pertinent variables. We're going to create a stack of images from the Xeno feed and analyze those. That stack will ever grow. We have here our defaults. We're just zeroing out everything. And then this is to handle the multi-threading issue. We have here the ROS2 Humble. It will allow us to take the sort of the wrapped feeds. The images are I guess you could say compressed, or they're in a format that we have to unpack. And this will allow us to do that without downloading the entire ROS2 ecosystem, which is a little overmuch. We're going to sign on to our Xeno router, and I always wrap this in try except because it can fail for various reasons. It's outside of the scope that we control. So here we have a configuration file that's Xeno is a library, so we imported that earlier, right? And then here we have our config. We're going to pull those Xeno configurations from the router to, or the configuration on locally here. Here is where we're going to actually tell it where is the router. So the connection endpoints, this is my setup, my Xeno setup. So this would be determined by your Xeno setup. And then here's our session that we're going to fire up with those configurations that we grabbed, modified, used. And then we'll see if there's any errors. Once we're subscribed to the Zeno session, we have to subscribe to a topic. I guess we're connected to the session, and now we got to subscribe to the topic. So we have here again this thing we're just calling sub, and it's going to declare a subscriber to the topic that we specified earlier. And every time it receives something from that topic, it'll fire this callback function, self.image callback. And then it'll let us know if there's a problem, let us know if everything connected well. Okay, load calibration is just loading up the details from the calibration file. Detect and match we'll get to later. Estimate pose, these are the two, like, hey, are these 2 points actually the same points? And so can we use those? If those are points that have translated, right? So that's not just wholly independent points, but points that translated. Then, what's our new pose? Let's estimate the pose change between point 1 and point 2. So we go down. We're going to process our frames. And in this case, since we're comparing a change, we need something to change. If we try to run this on a static image with nothing prior, it's not going to work. So we have to wait for at least one frame. Let's just go through here. And here's our image callback. So this is deserializing, getting the raw information out of the, sorry, this isn't the topic. This is what kind of information we are deserializing. It's a sensor message. Some of this code I think is vestigial from when I was trying to hook it up with the binaries, and I just couldn't manage to do that. I'm not really sure why I couldn't take these images and throw them to the binaries supplied by Stella-VSLAM. Would have been nice, but instead, our task 1 of this assignment required us to institute our own version of VSLAM, and then I wound up hooking this into that to get it to work. There's another demo that I had for video. I was able to get the video to work, but the image VSLAM just wasn't able, I wasn't able to get that working. And in the interest of time, I just went to my own. This is a lockup for thread safe operations. And then here we'll save our map. Here we'll plot our trajectories as we go. And here we'll run all of this. When we shut down, we're going to save our maps. I actually think maybe this should be in a different order. Let's change that real quick. Okay. All right. And then down here, we're going to instantiate our map object and run it. Okay. All right. Oh, and these interim things are in case the container shuts down before we're ready, before the script is ready. So I think we're ready to institute this with just one other thing to mention. The robot must be moving in order for the image to be changing and for that image to then be analyzed by VSLAM. So we actually have been supplied with another container. So we're going to compose up demo behavior, run it as Python. So once that runs, what it's going to do is take control of our robot and move it through this space so that we can start running VSLAM. So let's run our compose up map stream. Boop. Here it goes. And as you can see, there's nothing. Now let's start having our robot do something. And just for our own edification, let's have it do this. Okay, so it is moving, rotating. What's it doing? It's rotating. It's going over there. Don't go over there. Let's go over here. I'm just taking control. Well, maybe I'll take control in a minute. There it goes. Come on, little robot. You can see here it's trying to map its trajectory. It's maybe not handling rotations very well. I think there's some conflict here. It was working okay. Behavior. Okay, maybe we should Docker pose down, demo behavior, PY. All right, so let's just remove that. That would have made the visualization a little easier, but it's okay. Right. So this little red dot is where we are. You can see it is creating tracks. This is all being created from the visualization itself. Now, one thing you might say is, hey, this robot's moving really slow. Can't you just speed it up? I don't have all day on this video. You can play it at time and a half or double speed, but I have found that when I speed this robot up, the frames come in too fast and tracking is lost. And that's not great. The other thing is you can see here that this long straightaway is not well documented because the image isn't changing very well. In the original binaries that we were given, in the original setup for the Stella-VSLAM, they do a nifty trick, which is cheating, because they already have a known poses for what is expected. They can use those for ground truth. And by using that, they can actually translocate the bot a certain amount, and judging by the images, they can come up with a scale. Now, we don't have that ability ourselves, and I've tried various scaling features through this project to hard code, and this was the one that was working before. And as it is right now, you can see it's still going. The straightaway is not handled very well, but as the image environment changes, I just want, if you go back and you take a look at this down here, there's not a lot of difference in texture in this environment. When those textures do change, the map is updating, and that is great. But because the environment is so similar, there is actually not as much as we would like tracking. I would hope that with refactoring and some other bells and whistles, we could get a better result, but I do actually think, so let's watch that red dot. That red dot there is where we are, and now I'm just telling it to go back along the path that it came from. Now you would expect it to follow that path back fairly well, and it does look like it's tracking fairly well along that path. I have run this several times, and each time I get a slightly different result because of that lack of scaling that we can have. Now, if we added more objects and more richness in our environment, perhaps that scaling would change. But what's this bot doing? But this is the bare bones explanation of our system here. Now, to go into VSLAM a little bit more, just the tail end here of our environment, you can look it up, or of our demo, sorry. You can look up the math behind this, but it's actually pretty cool. It turns out that once you run SLAM, what you have is a matrix of rotational information and translational information. How much did you turn? How much did you go? Oh, you can see here again on the straightaway, it kind of lost that. It's not tracking like it did before, but that's because that straightaway is sort of in a different place because we didn't have a scale to keep everything perfect. If it was a real bot, we could get feed from the wheels and maybe have other things verify our ground truth, and then we could use that to perfect our system here. Unfortunately, the Docker containers that we have don't provide that information, except they do provide that from their own version of SLAM, which now that I have about a day to finalize everything, I have found out we are allowed to use. I did not know. I thought we had to do it ourselves. So as I explain VSLAM in abstract, let's tell this to go back over here, relatively the same place, and see what we get. Now, as I was saying, you can take a series of images and track these points. And as you use the rotational and translational matrices, you get an essential matrix from that. The essential matrix actually has 4 different solutions, and apparently it will always have 4 different solutions, and they're valid. They all work for reconstructing the world from this information. And depending on which one you use, you might need a little bit of an adjustment. I'm still wrapping my head around that. I did have previous work where we did have to, we were calibrating against the Kitty data set and had to readjust depending on what we were using. But as you can see here, you can track the path of a robot based on nothing more than the images it's receiving. And that tracking is not perfect, but as you run it more and more, you will get more and more of a world, of a view. That is my tutorial and demo. I hope you enjoyed.